And now, with great powers come great responsibilities, of course. AI bears an ocean of promises, but a wave also of scientific and societal changes. Let's navigate the change with one of the lead experts on machine learning, research director at INRIA and member of the French Academy of Science, Francis Bach. And if you have a question for Francis Bach, just post it on the platform. I'll be happy to pass it on by the end of the segment. And now, Francis, the stage is yours.
Thank you. So first, I would like to thank the GPI Summit organizers for inviting me. So I'm very impressed by all the work that has been accomplished, and I'm very honored to talk in front of such a diverse and distinguished audience today. So I am a researcher at INRIA, leading a joint team between CNRS, INRIA, and École Normale Supérieure. And my main research area is the theory of machine learning, but I do have lots of collaborations with other disciplines, and I interact a lot with the industry. But today is not about my lab, and what I will talk about today is progress of the AI community at large. Maybe a final disclaimer. I'm not an expert on everything, and there are many experts here who know much more than I do in some of the topics I will describe. So if you disagree, please feel free to ask a question after the talk. So everybody talks about AI. So this started in research labs, okay? Then it went towards all of the economic sectors, and now it has reached even family circles, and even last weekend when I was attending a comedy show. What strikes me the most is that most of the focus is on the future promises of AI, what it will do or what it will not do in 20 years, while people tend to forget that AI is already there. So there is one very successful, massively deployed AI system, at least commercially successful, which is advertising and marketing. So this is where the money is currently coming from, much of it in AI. This raises key questions related to the actual benefits to society and the global use of personal data. Should the AI community be part of it? I don't think so, but I'm optimistic, and my goal of my talk is to show that we can go beyond all of this. And I will first present the recent and current progress in AI and machine learning. Then I will look about the future limitations, because there are many of them. And then I will touch upon some topics that are of active interest for the GPI Summit, in particular with some working groups working on those topics. So first, why are we all here today to talk about AI? We're here because there's been a lot of progress recently. So I will not try to define what AI is. That will take me like most of my talk and launch like quite a useless debate. I just want to refer as AI as a set of tasks which are typically associated with humans and which are typically hard to code. So first example, which is like used by many of us on a daily basis, is face detection, which is used a lot in pictures. Other computer vision applications, so there is one which I like a lot from a colleague at INRIA, where you can predict quite unusual actions on images. So this is one key area is computer vision, but other key areas are in natural language processing. And now language translation, automatic translation is now being used on a daily basis, and it starts to work very well. So how does this emerge? So not by telling computers what to do precisely, but by the use of machine learning. So the idea is to start from some data where the task at hand is already done. So for computer vision, this means like millions of images which are labeled by humans. For NLP, this means like for language translation, this means millions of sentences which are already translated by humans. For advertising, whether you like it or not, this is your own navigation history on the web that allows companies to provide or to propose some advertisement. So you need massive data. You need massive computing power to deal with that data. And here we benefit from the various Moore's law that have been active for the last 40 years. But of course, you need a lot of progress, of scientific progress and algorithms. So at the end, intelligence, which I put in quotes because it's only as intelligent as the data that you feed it with, is a combination of models, algorithms, data, and computing power. So here I emphasize the role of modeling because there is no universal learning machine. So models and algorithms are similar between, let's say, language and images, but they are different, and you need dedicated models for every modality. So let's look at a few impressive results. And let me start with some work from my colleagues at INRIA, Bruno Lecroix, Jean Ponce, and Julien Meral, whose goal is to go from low-resolution images to high-resolution images. So, of course, existing digital cameras already does this. And you see what you see on the left is the output from a regular camera, which is not great. So what they did, and I think it's a very clever idea, is to use the fact that classical cameras now will not record a single image, but a burst of images, like a small video of 10 to 20 frames. And by aligning those frames, they can really denoise the image in much better way. So here it's a combination of computer vision modeling plus some machine learning. And again, it's fair to say this is very impressive. Also examples on text, where on the left you don't see exactly the map, and on the right you start to see text which becomes readable, and this can have many applications in many areas. So beyond smartphones and natural images, images come along in many areas which are sometimes classical, sometimes not. So on the left you see an image from a CT scan of some lungs. On the right you see some archived data from the Paris region from 1737, which happens to be a threat letter sent to one of my ancestors. So it is quite, those data are hard to interpret for humans, and there's lots of work trying to make sense of those images. Okay, so this is not a place where humans are very good at, but machines can provide nice interpretations. More generally, in computer vision, whenever you have some labeled images, we can do learning on them, and there are many applications that you can see everywhere. A bit beyond supervised learning, there is a possibility to start to have very complex and impressive behaviors beyond supervised learning, and this is the case with computer games, or Go or computer games. So on the left, I present the match between the world champion of Go and the AlphaGo, the algorithm by DeepMind that beat that world champion in 2017. Here, it started as learning by learning on human play, and then more and more they're using self-play. On the right, a much more difficult instance, which is the video game StarCraft. So it's much more difficult because you need to act in real time. This is only partially observable, and you have many actions that you can take. So here on the right, in 2019, the same company, DeepMind, managed to achieve human expert performance. So here it's very impressive, but all of those advances rely on the possibility of playing infinitely with itself. Okay, so this is possible for board games or video games, but clearly not possible in real life. Another area where there's been a lot of progress, and very impressive progress, and in an area which is a bit different from what we're used to, is protein folding. So proteins are key molecules for all human living organisms. Understanding them is key in biology and medicine. So proteins are sequences of amino acids, which themselves come from the DNA sequence, but the shape in 3 dimensions is pretty complex. And here I show on the left a protein which is used by plants to protect against bacteria. You can see a very complex shape on the left. And what DeepMind has achieved 2 years ago with the algorithm AlphaFold is to treat this as a huge supervised learning problem with proteins and their 3D structure, and they managed to be the state-of-the-art with a wide margin. Another nice aspect is the push for open science, as they release both the code to achieve those advances and the output of the algorithms on many proteins. So this has been a game changer in computational biology, and this opens up a lot of opportunity for drug design. So I will not describe all results in all disciplines, and audio has its share of nice results with like speech recognition being used every day. And if you want to play around tonight, I advise you to look at the website which is listed here, where a student of mine, Alexandre Defossé, has been able to take any pop song and separate the song into vocals, drums, and bass tracks. So this is very, very impressive. Also, NLP, I've seen, is shared of progressive with various models, with various names, in various languages, and I like to make some advertisement from colleagues at INRIA who released the Camembert version, which is the French version of BERT, like a very large language model. And these there are many applications that you can see everywhere. So now let's mention the future and limitations of AI. So first, you have to be careful when you predict the future. It's very difficult. So first, there are some limitations. So why don't we see like all those applications which are promised in self-driving or in health? It's because it's difficult. And why is it difficult? There are many reasons which I will describe now. So first, it's super obvious, but data is only applicable to AI, is only applicable to data and tasks which are available in electronic form. Obvious. And it's quite difficult to interact with the real world. And here, robotics has not been able yet to provide tools which can allow AI to be deployed on the fields, on the real fields. A second weakness, which is both a strength and a weakness. So AI relies at the moment on training from large amounts of data. So if you have data, it's fine. But if you don't, then it's difficult to do anything concrete. So here I've mentioned pre-training, which is a classical way to deal with problems with low amount of data by relying on related tasks with lots of data. But then, above all, prediction is not everything. So if you can predict if there's a face in an image, or if I will click or not in the ad that you show me, if I make a mistake, it's totally fine. But if you start to work in safety critical applications like driving or health or aviation, then you need to be able to certify your predictions, to estimate your uncertainty, and this we are still very, very far from having this like being available for the kind of models that are working very well right now. And finally, the classical curse of dimensionality, we cannot only rely on observing all possible outcomes of the world. Of course, learning is supposed to generalize to unseen data, but for some very complex tasks, like self-driving, which has to be doable in all conditions, weather, country, and so on, this remains very, very difficult. So associated with those limitations, there are a few research trends, and here I'm picking from what I know from the community, and we are working hard in trying to provide like solutions to those limitations. The first one is the need for supervised data. So this has been a focus of machine learning since the start. We know that relying on labeled data is complicated and time-consuming and costly, and there's been a sequence of X supervised learning, where S can be semi, weekly, or self. And this is very active and with lots of impressive results, where now the amount of training of labeled data is being reduced, and you can use vast amounts of unlabeled data. Then, as I've mentioned, learning does not exist only on a computer. You want to interact with the environment, and here there are many areas which are very active: robotics, control, and reinforcement learning. So we should expect a lot of progress in the next few years. But what I think matters the most is that we need to become a mature discipline. So now we have shown that machine learning and AI can be powerful, but let's now deliver as a full engineering discipline where we can understand what we do, provide guarantee, and provide these uncertainty estimates that I've mentioned earlier. We are still very far from this, and there's a lot of research trying to make AI like a real engineering discipline. Finally, I think I've seen emerging a lot of interactions between AI and machine learning and other disciplines or other fields. So there may be fields from computer science, like machine learning and programming languages, machine learning and cryptography, but also whole disciplines can be put in that X. For example, physics is the key exchanges between machine learning and physics, and the nice part is that they go both ways. You can use machine learning for physics, so trying to solve physics problems using the most recent learning tools, but also physics for machine learning. For example, many tools from statistical physics are used routinely to understand what we are doing. Plus, as a bonus, you get to meet new colleagues. But what I want to conclude on this research trends is that progress, advances are not limited by scientific advances. Okay, clearly, we need more than simply new research papers, and I will try to show how those limitations come in by going closer to two particular areas. So what about the promises? Okay, so close to 10 years ago, people were promising self-driving cars in 10 years. Okay, let's be fair, we are still waiting. So I don't want to spend too much time here because I'm not an expert in this area, but what I understand, what I know enough is that full automation is not here to arrive in the next few years. Maybe partial automation. Of course, you can get assistance to driving. That would be very helpful. Or you could imagine dedicated road infrastructures when full automation is possible. But it's fair to say that self-driving or driving is an area where humans are still much more advanced than machines. For example, in France, teenagers only need to learn with 20 hours of driving to be allowed to go on the road. I'm experiencing it with my daughter at the moment, so it's not 100% safe, but still far safer than any self-driving car that has been trained on millions of hours of driving. So here, I'm a bit pessimistic here. This will happen at one point, but it's not for tomorrow. An area where I think I'm much more optimistic is AI for health. So what we have seen during this pandemic is very important. Okay, so health is important, of course, and it's difficult. So here the potential is huge. Okay, so in any areas of medicine, we can have a potential for AI. In particular, many of when you go to the hospital in France, many of the tests are already available in electronic format, so there is a huge potential for things to be happening quickly. Whether it is for diagnostic, okay, for whatever disease you want to diagnose, for personalized treatments, okay, you want to adapt a treatment to a particular person, and of course, as I've mentioned, to do some drug discovery. I think we're all very much aware that this is important at the moment. So there are already many applications, but they typically take a lot of time to deploy. And this is due to a few bottlenecks which go beyond pure machine learning problems. Okay? So the first, which I want to emphasize on, is the gap between research papers and clinical practice. As an example, for COVID, there was a paper released in Nature in this March, which studied many papers that were trying to do COVID diagnosis or prognosis based on a chest imagery, like the CT scans I was showing. It turns out that from more of the 2,000 papers that they looked at, none of them was ready for really being used on an actual patient. There are many reasons to it. Two reasons that I think are important is a bias in small data sets. So you learn in a small data set, but it doesn't generalize to a new hospital. And so the lack of communications between data scientists and clinicians. Another hurdle is certification by health authorities, which is required, both for safety and also for reimbursement at one point. So this is needed, but this remains quite difficult because certifying an AI system is quite different than from certifying some drug. And finally, what I want to put some more emphasis on in the next slide is the need for sharing data. Okay, so as I highlighted with my COVID study, we need large data sets. Okay, so we have to go beyond a few patients, beyond one hospital. So they need, if you want performance, you need to share data. But if you share data, then you have some privacy issues, which are very acute for medicine, as personalized health data is very, very sensitive. So first, it's a complex issue, okay? Not only technical, it's technical, legal, and political. And today, I will focus mostly on the technical issues, assuming, which is not given, that legal constraints force me to look at privacy with guarantees, and that there is some political will to share some data. So now, how do we get to share data while preserving privacy? Of course, assuming that individuals are given their consent. So the first option is simply to anonymize. Okay, so let's take my medical record and remove my name, date of birth, address. This seems like reasonable, but this does not work. Okay, you can always infer most of the patients, the names of most of the patients, even if you remove the lots of names and dates from the record. So this may provide some quick solution, but this is not, I think it's not scalable, and it shouldn't be used in the long run. But now we can try to look at what the research community has to offer, and it has to offer solutions for privacy with guarantees. So of course, they will typically come with a loss in performance. It may be more difficult to implement. It may take longer running time, or it may degrade predictive performance, but they are there. There are two classical threads of research in this area. The first one is based on cryptography. The idea is that individuals or hospitals will send their data to some entity that will do machine learning and predict, but the entity will never be able to see the data and can only provide the prediction. This looks magic, but this does work. Okay. This is the beauty of cryptography. Then there is another possibility, which is called differential privacy, where you take your data, you add some noise, and because you add some noise to it, then you cannot recover the identity of the people. So in those two areas, we are not in a position yet where you can deploy those techniques efficiently with large models, but they start to work on simple models like linear models, which are still heavily used. But we are not there yet for the deepest learning models. As I've mentioned, there will need to be some trade-off between privacy and performance. Okay, so here, as a researcher in computer science, it's not for me to decide where we should put the threshold, where we should position ourselves in the trade-off curve. It's not for researchers, clearly not for companies to decide, and I think it should be the society at large that should decide where we position ourselves in this trade-off curve. Now let's look at the societal impacts of AI in two areas, the third being climate change. So first, let me remind us of the fundamental impact of information technology beyond AI. Before this, let's talk about the general impact of computers and machines. I mention this because often when we will talk about the environment, we forget to question why we need computers. Okay, so computers are useful in many areas. If you go to a hospital, it's full of computers. Teleworking has been made possible by computers. There's lots of positive impact. Clearly, there are some negative issues, like in every area, but I still think that the general impact of the information technology is positive. And if I thought it was not the case, I would switch jobs, in fact. But it has an impact in terms of environment. Okay, so it's hard to measure, but it's admitted that 4% of the greenhouse gas emissions are due to the information technology sector, and this is growing. On top of this greenhouse gas emission, there is a use of scarce materials, which I will not cover. But clearly here, there is also a potential for reducing the footprint, and I will of other sectors. It can help other sectors to reduce their own footprint, and I will mention this in one slide. So this was like information technology at large. What about AI? To me, AI is just the same. Oops, sorry. It has, in terms of general impact, beyond environment, some positive and negative impacts. Okay, so this is used in health in all areas. It comes with its own shortcomings. And in terms of environment, so this is a situation where it's hard to find the actual footprint of AI. So if you know a good study for this, I'd be very happy to have it. We know what will be that will require a lot of energy, what is consuming a lot of energy, but we don't know a precise global measure. So now let's look at the positive impacts of AI for climate change. So here I will talk under the control of the many people that have worked in this area. There's a very nice, 111-page paper with 22 authors, and also a 40-page report, very nice report, very complete, from the GPI Summit. So let me just summarize what I think is key in this area, how AI can help for climate change. So first, I don't think AI is a silver bullet for climate change. It's one tool among many coming from computer science and engineering. And AI has to play its role, okay, with some specificities, but I don't see it as a silver bullet. So three aspects. So in machine learning, we like to measure, predict. So clearly, we should we could use our talents at predicting, forecasting to measure the actual impact of climate change. This can be in the past, present, or future. I think it's very important, in particular, if we know climate change is there, but if we can't measure precisely where it comes from, it's going to be very hard to focus our energy on what really matters. So, to me, there's a strong need for better and precise measures. Then AI, like the rest of information technology, signal processing, computer science, can help in doing things better, okay, more efficiently. So you have all the smart X, smart buildings, smart cities, smart grids. The idea here is to get a finer control of all processes, industrial or others, like for heating and so on. So hereby, you can get easily 10 to 20% in many areas. So it is not going to solve everything, but it's going to help quite a bit. And finally, and this goes back to a more general discussion on AI, is that AI can help other sciences, okay, which are related to climate science. The idea here is to be able to combine model-based approaches, which are traditional in those areas, with data-driven approaches. So this seems easy to say, but it's quite difficult. And again, there's a lot of work at the moment trying to achieve this. But now let me focus on the potential huge footprint of AI, which is the impact of training large models. So as I've mentioned, for the advances in the natural language processing or for Go or for computer vision, you need a lot of training data and a lot of computers. So on the left, this is like an extract from a recent paper by Strubel and colleagues that tries to estimate the CO2 emissions of training a large natural language processing model. So on the top, you see in red the number of pounds of CO2 from an American person, average over, but not average, but over 1 year. And on the bottom, you see the number for training or for getting to a well-performing model. You see a factor of 20. Okay, so training a model can cost, in terms of carbon footprint, as much as 1 American in 20 years. So this is a lot. But there's even more worrisome. This is that curve. We have a Moore's law, but in the somewhat incorrect direction. Okay? So this is the over the years in the x-axis, and on the y-axis you see the computation, the amount of computation on the logarithmic scale. We see quite a straight line, and you can check. I've checked yesterday that it is multiplied by 10 every year. So it's really a strong Moore's law. So what can we do about it? So first, I think those like huge numbers have to be a bit mitigated because of the nature itself, the nature of machine learning. And this nature is that you don't, whenever you use a language model, you don't need to use that much energy. So you train once to get a good model, and then you deploy many times. And that many times could be on your cell phone, where battery life is an issue, or can be on the cloud, where you make a request. And this was the case for a while for machine translation. You put a sentence, and it goes on a server and goes back to you translated. What you have to realize here is that we are not doing nothing. Okay, so there are very strong economic incentives to reduce footprint, both in terms of money. So computers are costly, running energy is costly, so you want to reduce the footprint, but also in terms of battery lives. Okay, so there is a strong emphasis of the ML community trying to reduce the footprint also at testing time. This is related to the classical resource optimization for AI and more generally of computer science. So from the start of computer science, the goal was to do as well as we could with the least amount of resources. Typically, those resources are memory and time, and often correlated with economic incentives, and sometimes only correlated with environmental incentives. So there are a few specific research challenges which are associated with frugal AI, this part of AI that tries to be needing less energy. The first one is related to the energy efficiency of distributed algorithms. So typically, when you train those large models, this is not done on a single computer. You get like 10, 100 computers, and the hope is that by having 100 computers, the training takes 100 times less time. The idea would be that by designing new algorithms, it does not, the energy footprint does not scale also as 100. So this is like a strong research area. But here we need some accurate estimation of the actual footprint. And this is quite an open research direction with already nice breaks from people in Montreal. But finally, what I want to emphasize in this slide, lastly, is the maybe a need for some cultural change. At the moment, it seems to be that there is a race for bigger models. Okay, so we see it increase by a factor of 10 every year. Often, the increase in the size of the models is far bigger than the increase in the number of observations. Okay, so from a theoretical standpoint, it's not needed. Okay, there's no need to grow much faster than the amount of data. Clearly, we don't know how to do it, and we should try to look into that. Now, last part, what about employment? So I'm lucky to have been able to work with a colleague from economy, from École Normale Supérieure, Philippe Askenzie, and together we argue that AI is what we call a general purpose technology, a GPT. So what is a GPT? So first, we're not the only ones arguing this. It's now well admitted, but we worked on it 2 years ago. So what do you need to be a GPT? You need 3 properties. You need to be used in many areas. So I've just spent like 30 minutes explaining how AI can be used essentially everywhere. The performance has to increase with usage, and this is, you can argue this always, you can argue this as well for AI. If you get more automation and more AI, this will generate more data, so this will make the AI more powerful. And also it enables other innovations. So clearly, as I've mentioned it, machine learning and AI can be used in other sciences, but it's also a key driver of innovation in industry and all economic sectors. So now if we admit that AI is a general purpose technology, what can we learn from it? So now we can look at our colleagues from economy who have studied the classical phases of economic impact on growth and employment. So there are typically three phases. The first phase, that can last quite long, like 10, 20 years, is a phase where it's called adaptation, where the economy has to adapt to the new technology. You need to find new regulations, and there may be maybe talks about it today. You need to adapt the workforce. You need the technology to go from somewhat working to really working. This is the first phase with low productivity gains. This is like growing, but not at a very strong speed. Then there is a maturity phase where you see a lot of productivity gains, and then you end up with a saturation phase where you see a new technology taking over. So you may have guessed where we think we are. We are toward the end of the first phase, where the productivity gains are not huge. They are huge in some sectors, but really not as widespread as we thought. And hopefully, the impact of AI will lead to increased productivity. So now, if I say increased productivity, you may say, oh, this is going to destroy employment. Let's look into it. What is the actual impact on employment? So let me first mention a number which is cited a lot. So the paper by Fred Osborne from 2013, in fact, cited 9,000 times, not bad, states that at the end, in the abstract, 47% of total US employment is at risk because of AI. Is this really true? Okay, so personally, we think, and we're not the only one, that it is really like a problematic figure. In fact, they have already been proved wrong because they made that predictions almost 8 years ago. So what is the impact? Okay, so we can also look back in the past for other general purpose technologies. And first, the consequences of employment are hard to predict, but it never led to massive job losses. So there are several aspects to it. So I don't want to do like a class on economy. I'm not competent. But from what I understood, the job losses that may occur are typically compensated by creation in other areas. And creation of jobs comes from new offer and demand. So offer new types of jobs which are created by the new technology. And we can imagine like new types of jobs created by AI, and also more demand. And the increased demand comes from like all the people, companies benefiting from the new technology that have like money to spend on other things. Finally, maybe a quite speculative comment at the end, maybe AI can be more a solution than a threat. So at least in aging countries, economists stipulate that in the near future, there will be a shortage of workforce and that AI could be a solution to help in this area. So let me now conclude. So first, I try to argue that there can be AI beyond advertising and marketing. It's already happening. Like it starts in health. There's like a lot of sectors which are impacted, but clearly we should move and go beyond advertising and marketing. This requires some, I think, culture changes. One of them is related to the fact that, as I've mentioned, AI is typically done in collaboration with other disciplines. You have like AI in health, AI in the automotive sector, and I believe that many of the breakthroughs will happen at the interface between AI and other disciplines. So this means that the ML research community should really start to focus on what other sciences really need, and not only industry, and even less a single industry. Then to fulfill the promises, we need like more research, and more research. And I'm very happy that many countries decided to launch national initiatives, like in the last 5 years, and I've benefited from the French one in the last like 2 or 3 years. And I'm very proud that the President Macron announced this 1.5 billion initiative starting now, and I hope that the local research community will benefit from it. Finally, as I've mentioned, it's not only a matter of research. They need to work on the gap between theory and practice, and GPI seems to be very involved in this area. And I've mentioned this gap for health, but this is true in many areas. And what I want to finish on the education of citizens. So clearly, even if we manage to end up with the responsible and trustworthy AI, citizens may be reluctant to adopt new technology. We have seen it with like RNA vaccines, like in different areas. It's difficult to convince people. And here, I believe that education is a key issue, so that citizens can understand what AI can do or cannot do. And to conclude, I do think that what the work being here is crucial, and I've read yesterday through the reports that are going to be presented today. I'm very impressed, and I'm looking forward to hearing some of the discussions from the working group today. Thank you for your attention.
Thank you very much indeed, Francis. Please, I'm just right here. Francis, grab a seat. Come with me, and we'll answer one or two questions since we have a little time. First, I'm happy to learn that your daughter is way better than any autonomous vehicle when it comes to driving. Second, you've just mentioned a very crucial point, of course, which is the education of citizens. And as you also put it, of course, we don't embrace as citizen and user a technology that we can trust, right? So that the entire purpose of trustworthy AI and explicable AI that we'll definitely go to dive in during these 2 upcoming days. But what about the education of engineers and scientists themselves?
Oh, can you hear me? Yeah, so thanks for the question. So I think this is also very key. As I've mentioned in my talk, there is a strong need of interaction between, like, for the health sector, clinicians and data scientists. But this requires training. So doctors, clinicians need to know about AI, and data scientists need to know about like medicine and biology. So this starts to be done in the various like universities, but this is to me very important. We need to be able to talk with each other and hence speak the same language.
Absolutely. And then another thing that struck me actually when I was listening to the talk here, you probably haven't mentioned fairness. And I know it's crucial nowadays when it comes to really like trustworthy again and responsible development of artificial intelligence. So is fairness still crucial?
Sure. So, So I think like for any deployment of any like technology, you have to always keep in mind who the end user would be and how they will be impacted from it. In the context of AI with like training data, you have to be very careful that the training data are adapted to the representative of what's going to be, how it's going to be used in practice. But here, I would say that it's very hard and impossible to use training data which has no bias. The reason being that there is bias in our society, gender, ethnic bias in our society, and you cannot gather data with no bias. The idea here is to train engineers and practitioners to be aware of those biases and make sure that those risks of bias are mitigated by a proper use of the technology.
Thank you very much. We do have one question here in this very room.
Hello, Professor Bach. Thank you very much for your introduction and for raising many important points. I'm just concerned about one aspect of the introduction, which was that it had a very heavy emphasis on machine learning. But when we talked about some of the things that were introduced earlier, like the AI regulation and the impact of technology on society, then a much broader definition of artificial intelligence is important. Would you agree with that, or do you think it really is the machine learning that's the key aspect?
Okay, so First, okay, so disclaimer, I am a researcher in machine learning, so I tend to see machine learning everywhere, okay? So this being said, like much, if not all of the recent progress is due to machine learning combined with other things, okay? So learning has been present everywhere, but clearly there are more and more work trying to combine learning techniques with other ways of doing AI, but I don't see how you can deploy any AI system without any form of adaptation to what you see in real life. So that, I think, subject for debate, but.
We still have time for one question if you have, oh, we do have one question though. Oh, we do have another one. We just have time for one, unfortunately, because we have to go to break in like 2 minutes, but let's take this one with you.
Start with them. Right. So, could you comment on preparation of all these policy documents recently, including AI Act, UNESCO, OECD, Council of Europe, right? So it's a whole wave of documents being prepared, some of them legally binding, some more like soft legal documents, right? So could you comment a little bit on how do you see evolution and how this might impact our lives in the next years?
So here I have to admit like a total lack of expertise in this area. Okay, so I'm aware that regulations happening. I think they are needed to avoid like a really bad usage of the technology, but I think I don't know enough to answer that, but probably during those sessions today, this will be like explored more.
Absolutely, we'll definitely go to dive in regulation, like we never did bore over this upcoming 2 days. We'll have a